Hey, good evening, everybody. Thank you for tuning in to WATV Woodstock, New York, Channel 23, for another Wednesday night with the Conant Show. And as always, I'd like to thank our town for their support of our local access TV station, and I always like to acknowledge and honor our technician Paula Gloria Barton for all the expertise that she brings to the show. And so this evening I have a friend who I met through the movie theater, Bob Lavaggi, who turned out to be a filmmaker of sorts, and that's how we got to talking with each other, is about screening his medium that he's been working on, his stories and documentaries, and so I just kind of roped him into coming into our program here, and so Bob, tell a little bit about yourself.
Well, thank you for inviting me here.
Welcome to the Conant Show. Yeah.
Roping is pretty accurate. He called me around the middle of the day and said, "Can you come tonight?" And I never did this before. And this is kind of swimming in open water for me, but
Yeah.
Here we are.
Well, let's start with what you do in the community. This is a Woodstock Access, and I always like to rope my show into who we are in Woodstock and what we're about. So just that kind of gives you a little bit of something to bounce off of.
Well, that's a good start.
Okay.
I moved to Woodstock about 45 years ago, and I spent many years of my life designing and building houses.
Ah.
And then I retired from that and went on to puppetry with Arm of the Sea Theater.
Oh.
And then I recently discovered video and started working with video, and that led me to meeting George. So that's it.
All right. So we should tell our audience a little bit about that. Bob had propositioned me to rent the theater to screen a work in progress, so he could get a big screen view and critique of his new work. And I said, well, okay, sure, we can work something out, and we did, and it was actually quite enjoyable. And I gave my critique, and then a couple of days ago, he shows up. Hey, I got some more stuff I want to look at, and I'm like, well, okay, I'm in the middle of things, but can you do it now? And so we did that, and the subject matter was so much different than the first one that's what really piqued my interest. About, hey, you know what? I got a bit of a science mind, and I started thinking this would be great for a show. So that's why I roped you in. Besides needing a guest right away. So what I think I want to do now is, why don't you tell us a little bit about the theoretical sciences that you're into, and share with where that began, perhaps.
Can you pull his mic down a little? I had it on the bobby pin.
Uh-huh.
Can you help him, George? Just.
You want me to go?
Is there no more bobby pin there?
There's a bobby pin there. Yeah. All right. How's that?
Good. Thank you.
Okay with me.
You getting a signal?
Yeah.
Yeah.
Okay. All right.
All right. Well, maybe to go back to Woodstock beginnings a little bit. 35 years ago, I came up with an idea which was inspiring to me. With the diminishing resources on our planet, I was looking around for resources that we could waste without worrying about compromising our well-being. And I happened to get the idea, time. We've got tons of time. We can spend it all we want, waste it, design it, twist it, bend it, make music with it. But it doesn't cost our natural resources, doesn't consume natural resources. So this seemed like a good idea to me. If everybody in the world, or at least whoever wanted to, could get their, could consume time rather than natural resources, that would leave more for our followers. I had that idea, and I wrote an essay to the Woodstock Times, which sparked a little bit of dialogue. And a friend of mine told me, if you're going to write about time, you'd better read Albert Einstein first. So I got a book and started reading Albert Einstein's writing. He had always been he was a childhood hero for me. And now I was going to find out why he was my hero. But I didn't get far into his book, into his writing, before I discovered that his theory is based on the idea that the speed of light is constant. The speed or velocity of light is constant, or the same, for all observers moving relative to each other. And I was not prepared to buy that, because it doesn't make any sense. That is basically saying that if light is coming towards you, and one person is going towards the light and one person is moving away from the light, that the light will pass the two observers at the same speed. And I don't accept that. It doesn't make any sense to me at all.
Could you restate that for me one more time? I want to hear that again.
Okay.
So,
Here's a light shining. This one. All right. Here's a light shining at the two of us.
okay.
You're moving towards it. So why don't you do
So
that?
I'm going towards it.
And I'm moving away from it. And the light is passing you and me at the same speed. That's Einstein's principle. The principle of special relativity is that the same light passes the two of us at the same speed.
Though we're going in different directions.
Exactly. That's the principle.
That almost bespeaks a electromagnetic wave field phenomena more than a linear movement of a physical thing, like a light particle. If it were a light particle and it were moving linearly and in effect catching up and surpassing me in my direction, and then leaving you in the dust, so relative to each other, if you're going in this direction and the light is going in that direction, then differentially this light is going faster than coming up to me and catching up to me. Is that making any sense? Or am I missing something?
No, I guess I think I understand what you're saying. Well, but you did include differentially it's going faster. Yeah, I think that's what you said.
Yeah.
So as long as you're recognizing that it's going faster, that contradicts special relativity.
That's what I was looking to do. Yeah, okay.
Right. So we're both on the same page there.
Okay.
Logically, if you're going towards the source and I'm going away from the source, it would pass you faster.
Now, say that again. before I go into my next thought.
If you're going towards the light source,
Right.
and I'm going away from the light source, then the light will pass you faster.
Yes.
You will
It's
be...
the train station experiment in a way. Sorry. So if I'm standing on a platform in the train station, and the train is, passing me, and I'm stationary, relative to me, it is moving at x, right? It's moving at x amount of speed. But if I'm, walking or jogging opposite to the direction that it's moving, relative to me, it's moving x plus.
Right. Right. Well, that's what we experience all the time.
Right.
And that is referred to as Galileo's principle of transformation. Now, Einstein says that at slow speeds that holds up and is true, but at fast speeds it doesn't hold up. I don't buy that, because if it holds up at slow speeds, the faster the relative speed is, the more dramatic the relative speed will be, from a logical point of view. Do you follow that?
Right.
For instance, if you're traveling half the speed of light towards the light source, the light will, or if you're traveling towards the light at the speed of light, that would be, the 2 would make the speed of 2c, or double speed.
Right.
And if you're moving away from the light at the speed of light, the light will never catch you. It'll never get to you.
Right.
Yeah, you'll just both be moving at the same speed. That, again, is classical relativity, and Einstein says this is all wrong. The fact is, number 1, nothing can go faster than the speed of light. And number 2, no matter how fast you're going, the speed of light will always pass you at the same speed, 300,000 kilometers a second.
That almost seems illogical to me.
Even physicists who believe it's true admit that it's illogical.
Does this come into play with the idea of spooky action at a distance?
I don't know what spooky action
This is
is.
one of the Einsteinian thoughts where in explaining gravity, that a very small measurable force can have an effect in a very, very distant location.
Right. Oh, all right. I understand that, and I've heard that many times.
Right.
In all the reading I've done. As far as I'm concerned, the use of the word spooky in science is unacceptable.
Yeah, that's
to
a
me.
red red flag right there.
It's totally ridiculous. Anybody who uses the word spooky in science is just being poetic, and or theoretical, or not theoretical, theatrical.
Theatrical.
Or dramatic, but it's not a scientific term. What is the value of spooky? Is it worth 10 or 20? What is spooky?
Well, I think
poetic.
I'm kind of scratching the bottom of my memory barrel here, so because I'm not a theoretical quantum physicist or scientist, but I do like to study the stuff, and if I'm remembering things, the idea being, well, there's like scalar wave phenomenon, and when you one maybe physical example I could come up with is a tsunami, because you have amplitude, you have a body of a material, in this case water, and somewhere in that field of water is a perturbation, and in that perturbation, a wave is formed.
Okay.
And the wave starts out maybe aggressively but very small, but as when you drop a pebble in a pond, you see the concentric circles.
Right.
And as the circles are generated and then emanate out, the amplitude increases.
Okay.
The wave gets longer, it gets slower in frequency,
Right.
but greater in amplitude.
Yeah, you and I have both
So when-
seen that many times throwing pebbles in a pond.
Right. So as that ripple becomes ever greater swells, higher swells and lower valleys,
Yeah.
and it approaches a landmass, and then the shallowness of the ocean at that point is what becomes the driving resistance to
Yeah.
bring the water up
Yeah.
as high as it does in a
Yeah,
tsunami in a tsunami event.
Mm-hmm.
So here we have a perturbation at one location that does relatively nothing, but at the end result, 1,000 miles later, is this huge wave and huge amplitude. So there's this quality in space and time that I think incorporates some of that idea of something happening here, but it having a great effect kind of almost unreasonably over in some other location. And I don't know, I'm missing so much in between here.
No, but there's enough there for us to talk about.
Yeah.
You've made a metaphor there between the ocean on Earth and outer space.
Okay, yeah.
There's certainly gravity in outer space whenever you come close to a mass. But there's a lot of outer space that has low gravity because it's far away from mass. And the conditions out there, there are three dimensions: length, width, and depth. It's all space, all over.
Right.
And I don't mind throwing in time there because we move through time, and so that I don't mind recognizing that as a dimension. But that is outer space.
Okay, so there's I shouldn't interrupt. Keep going.
That's very different from the conditions here on Earth, which is a globe where gravity is pulling in all directions and pulls on water, making a flat surface all around the globe and distinguishing itself from the air, gas above it, wherever we are on the planet.
Mm-hmm.
There's an interface between the water and the air,
And that's where surface tension.
and there's surface
Happens.
tension. There's no such surface tension in outer space. It's space here, there, everywhere is space. There's no plane where two different physical phenomena
Right,
are interfacing.
Now that's interesting because in many representations of space-time curvature and stuff, you see a planet on a plane with this field bending around the planet, or this plane bending around the planet. And I noticed, was it on your book cover or something?
Yeah.
Taking the curve out of space-time or something, or how did that go?
Unwarping the space-time.
Unwarping the space-time. Can you?
Unwarping
I'm
the
curious by that. That really
space-time.
grabbed my attention. Where are you going with that?
Well, you did, just to take one thing at a time,
Yeah.
in order for Einstein's theory to work, he had to express metaphorically the relationship between that plane. He had to create that plane in space so that he could express gravity using that plane. But that's totally an invention of his imagination, and perhaps his genius is that he was able to visualize that imaginary thing. And once you visualize that imaginary thing, then his theory mathematically adds up. As long as you include that imaginary situation.
Right.
So in a sense, he was like making a copy of the condition here on Earth, where there is water and gas, and the two interface, and they play with each other, and they play against each other. If you ask me, that does not happen in outer space, except in Einstein's imaginary world.
Right, and we have these things called models.
Okay.
All right, and there's a few curious models out there, and I really like the traditional model that we get of the solar system when we're kids, and I think, I don't know, I started getting earth sciences and maybe 9th grade, 8th grade, like that, at least when I was in school. And it always shows our solar system on a flat plane.
Okay.
And the depiction of the sun and the planets tend to show a kind of uniformity, a regularity about it that serves a purpose to illustrate. Okay, well, here's our central star, and here's the planets, and I can remember that the text of the book would say, well, you can't really show on a page the scale of this thing.
Yes.
Because our star, our sun, the Sol, is nearly 1 million miles in diameter. It's like 800,000, 900,000 miles in diameter.
Right.
And on our astronomical unit, 93 million miles from Earth to Sol, is there's a proportion there, right? So I think it was like 1 to 100 or something.
I don't know.
But anyway, that model is very kind of static in a way.
Okay.
And then, I don't know, about 5 years ago, you gotta love YouTube, you gotta love the internet, because people post all this great stuff. And there's now a new model that they want to show the kids, and it basically shows the sun on its path through space.
Okay.
If we were to give Big Bang a credibility here, that everything is moving in space away from a central point, the singularity.
Yeah.
Right. So then, our whole solar system is being dragged along in this movement, in this general movement of an inertial field.
Okay.
Okay. And in that condition, you don't have a plane. What you have is something more akin to a comet, and these, this debris field sort of cycling around this object going through space. So that's the new model that we're looking at. So those orbits don't track. It never occurs in the same place ever again. So we're all corkscrewing through space at some ungodly speed.
Yeah.
And one of the interesting things about this is, trying to understand the scale of the cosmos, the scale of, say, of our local universe, of our galaxy even, is a thing called parallax. Right?
Oh, okay.
Parallax is when you are observing something, and this is what gives you depth of field in your vision. You have 2 points of observation in our binocular vision, and it is because we have 2 points of observation, the singular object that we're looking at gives us a depth of field because
Right.
we're looking at it from two.
Okay, good.
All right?
Yeah, I'm familiar with that.
All right, so when you have a condition out in space of the parallax of a star is oh gosh, now I'm scraping the bottom of my memory barrel again. Okay, I'm gonna have to dump that thought for a minute. So, in this movement of our solar system, right? I'm trying to connect how parallax fits in with this. There should be measurable changes even though the immensity of it, because we are explaining that like the precession of the equinox, right? Our star field from age to age changes over time.
Okay.
You know, Orion changes in its orientation. The different constellations are prominent at azimuth on certain days of the year. Say, you know, let's the December 22nd, or the equinox, or whatever. The Pleiades will be at midnight, 12 o'clock high, or whatever, on a certain time, certain date.
Right.
But that changes over time. It doesn't stay static. And they call that like the age of Pisces is now, we're now going into the age of Aquarius, and that means that we will have a new orientation of the stars to Earth, you know, in measuring time.
Well, I think we certainly have, it's a new situation out there continually. It's continually changing.
Right.
And I have no trouble agreeing that the shape of the space is changing. The distance from some things is getting larger. The distance to other things is getting smaller.
Now, I was thinking measuring. You know, I like to be able to measure my world so I can test the theory.
Yeah.
Right. And one of the things that I've read is about astronomy that's now kind of kicking the can for a lot of these astronomers is that the redshift, right? So you have redshift, blue shift in measuring distance and speed and directionality of stars relative to us. Are you familiar with that at all?
Totally.
Okay.
Yeah,
could you explain that for our audience a little bit? What that means?
I actually had a long conversation with Bob Berman on this subject.
Great.
About 3 or 4 years ago. I presented my theory on relativity, basically that I don't agree with it.
Yeah.
And of course, Bob is, it's part of his world.
Yeah.
So he was not going to budge an inch on that. And so we had a very respectful conversation for a good long time. And we ended agreeing that we disagreed.
Yeah.
But this notion that the universe is expanding at a greater and greater rate, and that we know that from looking at redshift. I'm not convinced by that. I'm not persuaded by that at all. For one thing, it presumes that we're right in the center. And it also presumes that there's a finite size there. And I don't think that the universe is finite. I think it's infinite. So, saying that off the tip of my tongue, it sounds a bit arbitrary.
Yeah.
However, it's my opinion that light can be interfered with. That certainly when light hits something, a mass, it stops. Unless it's translucent where it can flow through. But even when light flows through a glass, it flows through the glass at a different speed. And it, who knows, perhaps the theory is that it emits from the glass back at the speed of light, 300,000 kilometers a second. I'm not arguing with that.
Well, I'm not arguing with it, but I question it.
Okay.
Because
Okay, well...
just as an idea.
Yeah. So for now, I can leave that hanging.
Okay.
The most important thing is that this universe has mass in it. Every star out there is mass, and there's no reason to think that those stars don't have planets going around it, those going around them. So I figure if light is traveling for millions or billions of light years, that it starts to get deteriorated. Its speed gets deteriorated by all that it encounters, all the particles, all the dust, all the quotes, dark matter.
I was hoping you'd bring dark matter up.
Let me finish one thought before I go on to dark matter.
Sure.
Whatever there is out there between here and 1 billion light years from now, there's no reason not to think it's possible that there's enough out there to lug down the light so that it shifts red. And beyond that, there's just the same as what's here, except that stuff is so far away that it lugs down to invisible before it gets to us. So that's why it looks like we're sitting in a universe, a finite universe that has an edge all around it that's shifting red, and we just happen to be in the center of it. To me, that just means that the light is being affected by circumstances in outer space approximately the same amount no matter what direction it comes from.
Well, yeah, that's good reasoning. I agree with that.
All right, so then dark matter. I feel like scientists have this desire to make things really complicated. And in fact, things may be much more complicated than we can comprehend. However, we know that matter is dark. We know Earth would be dark, the moon would be dark if it wasn't the sun was shining on it and brightening it up, lightening it up.
Right.
The sun is the only source of light in our solar system. Everything else is dark. So what is the big deal about dark matter?
It's just matter.
It's just matter.
What's the matter, you?
What's the matter, you?
What's the matter, you? What intrigued me about the idea of dark matter is the idea that, and it harkens back to an ancient idea, but what got astronomers' attention in, say, the past 100 years is the idea of a singularity and a big bang and everything moving away from each other equally doesn't work. What they're finding is they're finding things folding back. They're finding it more like eddies and streams and rivers. They're finding groups and clusters of galaxies even, not even just star clusters, but galaxy clusters that seem to be moving as though they're in a medium, much like twigs and stuff in the currents of a stream or a river and water. Mm-hmm. So the reasoning became, well, no, it just there's got to be something there that's holding that together for it to all be moving together. So it was kind of, in my mind, it was an act of desperation. Okay, we can't explain it, we don't know what it is, but we can call it dark matter. It's like, okay, let's just give it a name,
right?
And then,
be done with it.
And then explain it later. So that's one my feeling about that a little bit. But more interesting to me is, okay, I'm going to go out on a limb with you. I have a memory of being on a spaceship with aliens when I was a little kid.
All right, let's go.
Okay, and they picked me up, and I was about 3 or 4 years old. My brothers were supposed to be watching me, and the only corroborative thing that I have that can nail this down is that maybe it really did happen, and it's not just a fig Newton of my imagination, is that my older brother Ray was on the same craft the same day, and we didn't talk about it until I was in my 20s and he was in his 30s, and we both just had kind of a real solemn moment about it. He didn't fare very well, and he freaked out, and they put him back in the house. And I should tell you a little bit about what happened here. I was down in the backyard, and you see, I was the youngest of 9, and my 7 older brothers kicked me around like the football. So I got picked on a lot. I was the little brother. I was the pain in the butt, you know, and I would always be sneaking away from them because I didn't like the treatment that I was getting. So I would play with bugs and ants and do all that kind of stuff that a little kid does in my own little world, in the safety of my own little world.
Yeah.
And on this one day, I remember looking up, and the sky was this really weird cobalt blue. And something grabbed my attention over the pear tree, and I look in that direction, and I see this craft. And I think to myself, or I think to it, I know what you are, you're not going to get me. And then I hear in my head, oh, yes, we are. And so I hit the deck, and I'm trying to crawl, and I'm thinking, okay, if I can get under these trees, they were hemlock trees, and I could get tangled in the branches, and they won't be able to get me. And as I had that thought, from the base of my skull to the tip of my spine, I go numb. I had rotten older brothers. You know, if you test a 9-volt battery, you know, with the 2 poles, and you put your tongue on it, you know, you get a flavor, right? The flavor of electricity, right? But that's the flavor I had in my mouth when this was going on. And I come off the ground. They get me in the craft. I watch the ground fall away. I watch the house fall away. And it was just like a sci-fi movie, and the aperture closes underneath me, and now I'm talking to a group of people. My brother, on the other hand, I love to tell this story because his experience was very different. They got him from right inside his bedroom. And he was picked up by the same kind of energy field, and he was actually drawn through the wall of the house. And as he's going through the side wall of the house, he said, I could actually feel, I couldn't tell if I was passing through the wall or the wall was passing through me. Okay? And then they took him through the side wall of the craft and into the craft, and he completely couldn't handle it. He was 12 years old. You know, he's some 8 years older than me, so he was about 11 or 12. He loses his cookie, and they put him back in the house. And he to this day, has never been able to really integrate with our norms of society. So Ray's had a tough time in life, you know, on a lot of levels, as an artist, as creative, hyper-intelligent, and all this kind of thing. So my meeting with them included a discussion about space. And I said, well, why me? Why are you picking me? I said, well, we're not picking just you. We're picking lots of kids. We're picking lots of people.
Okay.
You know, it's just that you don't know fear yet. And they said to me, the shape of your mind. And that bothered me for a long time. What the heck does that mean? But that's a whole other conversation. So the basic message is they were trying to communicate with humans that there are 1 million species out there in space watching Earth because we're playing with nukes. That was the message. Because we're blowing nukes off, we are considered insane and doing illegal stuff cosmically. Because their explanation to me was, space is not a vacuum. Space is not a vacuum. It is full of hydrogen ions. And an atomic detonation outside the magnetosphere of a planet can detonate all creation, wipe out everything across the board, everywhere. The universe goes kaput, and there are 1 million species locally that don't like that idea. And we have been under quarantine ever since. So that was the basic message, is that we have to clean up our environment. We have to, you know, throw the bums out of, you know, that are in control of us, and take charge of our planet in a responsible manner. Or there could be intervention, and they say they don't want to do that either. And various levels of intervention, the human and alien cooperation could happen. There's a lot of options here, but the best option is that we simply grow up on our own, so that nobody has to babysit us for 1 million years. That's the thing. But the piece of information that I found really intriguing is that space is not a vacuum. It's full of hydrogen ions. And I wonder had you ever encountered that thought before?
Well, I have to say that what you're saying is much more interesting than
that?
Than science.
No.
I've never encountered. How old were you when you had that experience?
Probably 3 or 4.
I never had that experience myself, so I can't speak from experience.
Mm.
And what did you say? What is space full of?
Hydrogen ions.
Hydrogen ions. I don't know. I
Well, let
don't-
me put it to you this way. The reason I bring it up is and this is probably going to piss off a lot of my science friends, is I've been looking into the flat Earth theory.
Well, you know,
And-
between you and me, I've been pissing off my science friends and all
Yeah.
the whole scientific cadre
Yeah.
is irritated by me. Although there are a lot of us who disagree with Einstein.
Yeah.
I was very surprised to discover that. But flat space, is that what you were?
No.
I-
It's again, it's about measuring our world with hard science, actually measuring the curve.
Okay.
All right, because the curve
Which curve?
of the Earth.
Okay.
Curvature of the Earth is measured for every 1 mile. There is 8 inches of drop squared. So theoretically, the curvature of the Earth at say 24,000 plus miles at the circumference,
Yeah.
right, of the equator,
Right.
translates to 8 inches of drop in 1 mile. In 2 miles, I think it's 32 inches or 16 inches, but it's an exponential thing. So in other words, here's your, say, a plane,
Yeah.
and then you have the circle underneath it, right? So as that circle falls off relative to the horizon,
Yeah.
things drop away very quickly. So that's why, they say, well, when you're at sea, on the horizon, on a still day, the object that you're watching that leaves you from the bay,
Yeah.
say with these big ships, and there's people with these great cameras now that track this stuff, after 8 miles, it disappears below the horizon.
Right.
Well, the modern videography isn't showing that.
What is it showing?
It's showing they're just watching the object. In this case, this one video out of Florida, out of Tampa, Florida, this civilian, she's not a scientist, she just got a really good camera, and she did this experiment just for herself, and she tracked and watched this super tanker for probably at 45 minutes. And you can just keep, it just gets smaller and smaller and smaller. She keeps zooming in on it, and you keep seeing the whole object.
Mm-hmm.
And when it finally disappears, not by subducting over the horizon, it disappears because the water and the air have a convergence zone,
Okay.
much like a mirage. So what happens is where the ship and the water make contact slowly disappears and just becomes invisible.
Okay.
But the top relative to the water stays the same, but that convergence zone eventually swallows it all up. So you never see anything go over a curve. What you see is it just gets so far away that the atmospherics overtake. That's that's why I'm calling the convergence zone. It's a phenomenon of the atmospherics. Vapor in the water, reflectivity, and it's just so far away. But so that's one. The other one.
Flat Earth. That's what you were talking
Yes.
about. Flat Earth.
Yes, it's a very upsetting concept for a lot of people, and I'm only exploring it, because there are a series of experiments going back to the 1850s and beyond that tried to measure, because you should be able to measure it. And there is no super engineering that takes into accounting curvature of the Earth. All the superstructures just plumb, no matter how big or how far apart. One is the Lake Pontchartrain Bridge. It's 22 miles long. In 22 miles, there should be some 237 feet of curve, of drop. And there's no accounting for it.
The Pontchartrain Bridge, that's down there in New Orleans.
Yeah.
So you're saying over the distance of
22 miles.
22 miles, the scopes that are used to
Measure that. Right.
don't express the 8 inches.
That's only 8 inches in 1 mile.
Right. Well,
And 22 miles, it's 8 inches squared per mile. So that's an exponential number. It gets much, much bigger very quickly. Another example.
Well, before
Yeah.
you give me another example.
Well, the other example that's.
Before you give me another example.
Oh, yeah.
As much as I am contrary to much of science, I would not be able to accept what you're saying on face value.
Yeah.
Straight away. I'd like to get more reference from other places.
Absolutely.
But right now, on that theory of yours.
Oh, it's not my theory.
No,
I got roped into studying it out of curiosity.
On the theory that you just presented.
Yeah.
I'm as reticent as I am about special relativity.
Yeah, yeah.
One thing that I find is a sociological phenomena. All of us are trying to enchant the world with bizarre and spooky theories.
Right.
So when science uses spooky theory, I say to myself, that's just human nature trying to be enchanting. So I have to bring the same skepticism to what you're telling me. It sounds like spooky.
Well, you do know why I brought this up. Because
no.
when you were talking about the globe earlier,
Yeah.
and how the water seeks level,
Yeah.
and so it's seeking level on the curve.
That's right.
And the experiments that I'm referencing don't show the curve. It's easier to demonstrate flat than it is to prove the curve with physical measurement.
So let's see. I just
that's,
want to get something straight here. Someone has presented this theory, and you're presenting me with this theory.
Yeah.
We might chalk it up to me being ultra indoctrinated to the idea that the world is round. But right here tonight, on this show,
Yeah.
I'm not going to let go of that for anything.
No, and I wouldn't.
Maybe next week,
I wouldn't ask you to. I'm just saying that I am finding as the older I get, the weirder it becomes.
But it's a weirdness. Physical existence is what it is.
Yeah.
And it doesn't care whether it's weird or not. Weirdness is a psychological phenomena, and we all love weirdness. We all love it. It's enchanting. It's magical. We like to go there. And
it's like, why do we like to be scared? Like in a scary movie. Why?
Right.
It's a whole.
Right. Well, it feels good. The
Attraction.
adrenaline,
The
the
adrenaline
adrenaline
rush,
going
yeah.
through. You'll like that. It's like drugs. But many people who I have the conversation on special relativity, the thing that upsets them, because they're not physicists,
Yeah.
what upsets them is that I'm taking away the magic of time dilation. At least suggested in special relativity is the possibility that you can move in time. And if you take special relativity away, then you take that away. And I find many, many, many people are disappointed, or they just reject the fact that you can't go back in time. So I think that's where Einstein has kind of found his niche in enchanting and creating this magic, this spookiness. And he has totally enchanted the world.
Yeah.
Now, probably 60% or 80% of the people who I discuss this with are not physicists. And they don't believe what I'm saying when I say that Einstein's theory depends on the notion of constancy of light. And they don't understand what that means. They just say, oh, light's constant, big deal. I'm not denying that light isn't constant relation to its source, and maybe for 1,000,000 light years, but eventually it might slow down. But I still think that the speed of light is relative to observers who are moving, which immediately closes the book on special relativity. And people get very disappointed.
Well, one of the arguments or one of the ideas I explore about light is, well, what is it? What is it? Is it a particle? Is it a waveform? Is it something? Is it a hybrid of the two?
Well,
and there are great efforts being made to understand various radiative energies in space. They have these deep tunnels for capturing neutrinos on film and this kind of thing, and that there are gamma rays and ultraviolet rays or X-rays and various, and these all have different speeds too, or are they all varieties of light that go at what'd you say,
300,000 kilometers per second.
300,000 kilometers per second. And, or are each of these particles or waveforms subject to different limiters? I guess what I'm postulating here or questioning is the radiative quality of, say, the light that we see in the spectrum that we can see it, is it behaving with the same rules as, say, gamma rays or X-rays or neutrinos or?
Well,
have you looked into that at all?
As far as I understand from physics, they're all electromagnetic waves, and they all travel at the speed of light.
Okay.
Radio waves and all of those waves. Now, I don't know that that's true, but that's not my area of challenge. It doesn't matter to me if different things travel at different speeds. Whatever anything travels at, speed is just a concept. It is not. You can measure the speed of a fly flying across the room, because there's a fly there that you can measure the speed of relative to you.
Right.
But you can't measure the speed of speed. You can't measure speed. You can't grab hold of it and measure it. It's just an idea. It's
the inertial field that you were talking about in your video the other day,
yeah.
which I had hoped we could show, but that's all right. Let me just check the time. All right. So in a condition of inertial field, I remember driving with Mom and Dad and my brothers on these long trips, and we'd be in the car 65 miles an hour, and somebody would throw a ball up, and it would behave relative to the car and not to
the outside.
The outside.
Yeah.
Because everything in the car is moving with that same.
We all have experienced that.
Right.
All the time.
I'm just reflecting on that because in your illustrations, of the hammer driving the nail, right?
Yes.
And you use the little field. You created
an energy field.
An energy field that kind of depicts this visual of inertia. It's the first time anybody has, that I've seen, depicted inertia as a field.
Well, thank you.
And how it got translated from one object to yet another object and then dissipated perhaps in the third object. So what I'm trying to connect here is I had never thought of this before in terms of being in a car moving and everybody and all the objects in the car are we're all now in a shared field.
Yes, right, we are. Just like we are here in this room.
Yeah.
Flying through space at 30,000 kilometers a second.
Now that have you had anybody critique that concept of the inertial field that as you showed it in that video?
That I just came up with that idea this summer.
Really?
And
well, I think it's a fabulous idea. Just so you know, I'm really enamored with it.
I'm very excited by it.
Yeah.
And I would like it to get exposure, but maybe this is the first step.
Yeah.
Chatting with you about it tonight.
Sure.
But it's you're able to visualize it. Obviously, the blue is just a symbolic representation of what I imagine is happening there.
Right.
Now, Newton said that he couldn't imagine what gravity was. And then Einstein jumped on that and he said, well, gravity is this space-time continuum. And I'm saying that gravity is invisible, it's just there, and it surrounds every piece of matter that exists. Mm-hmm. And it does all the things that Newton measured it doing. It's just that he thought gravity had to be transferred there. And Einstein said, well, yeah, it goes there at the speed of light. And I'm saying, no, it's there all the time. Gravity just is. And inertia just is. Even though it's invisible, it is. And it just crossed my mind that the fact that there is something there which is, but you can't see it, is really at the bottom of this whole, of the whole confusion that we have right now. And so if Einstein made space-time warp, that's one answer to that question. But it's not that complicated. Gravity just is.
Well, we've just eaten an hour. I told you it was going to go quick.
It went fast.
It went fast, and so
We have 2 minutes.
we have 2 minutes, and what can we do in 2 minutes?
What about Admiral Byrd? Anything you can say on him going to the South Pole?
Well, Admiral Byrd was well, the only thing I can connect with that right now. I mean, he did explore some incredible phenomenon, in his journeys that he recorded. But to make it personal, I had a best friend when I was about 8 years old, Robbie D'Ambroso, and the D'Ambroso family had an uncle, either an uncle or a great uncle, who had been on some of those expeditions to the poles as a shipmate. Mm-hmm. And he came back with stories that he shared with the family that I got from Robbie when I was a little kid. So I was real little, and he's like, yeah, my uncle was on this expedition to the North Pole, and they got in trouble. Things didn't go right. They were running out of food. And they
on their expedition.
On the expedition. Yeah. And it's a well-recorded event. I mean, these expeditions were dicey things, and in the earlier ones, the equipment wasn't as good as the decades progressed. So,
right.
So when Admiral Byrd was a real young man, which is when this was going on, they ran out of food, and they were locked in the ice. Mm-hmm. And out of Providence, whatever, they found a mammoth, frozen, solid.
Wow, very convenient.
And, you know, we are told that the mammoths, you know, went the way of the albatross, you know, 12,000 years ago. But they found this mammoth, and it was frozen solid, and it was good to eat.
Wow.
So they were eating on some of this mammoth. And there you can actually get mammoth steaks up north. You know, they still find them from this cataclysm that killed them all, and then flash froze them. But here's the curious thing. The curious thing is that there is a bacteria that lives in the gut of all of us, all mammals, all living creatures. And that bacteria is very much a clock to the point of when you die. Because the moment you die, this bacteria is activated to start the decomposition process. So that's what the forensic guys do when they want to know, well, how long has this body been dead? And right? So when they're trying to, you know, do crime, solve a crime or whatever,
Right.
they look for that signature.
Yeah.
All right. So what these guys found is this, you know, multi-ton, hair-covered body of flesh,
Okay.
hot meat,
Yeah.
was frozen so quickly that the buttercups in its mouth were still fresh. The gut bacteria that is the timer for the moment of death hadn't a chance to get activated.
Okay.
And this is what spooked those guys. Now, and this is a legitimate use of the word, because they want to know what kind of event, how cold, how fast, and how cold did it get to flash freeze, you know, 12 tons of hot meat that has hair on it.
Right.
And so while these guys are dining and, you know, having their lives saved by this, you know, fabulous creature that, you know, was 12,000 years old and still good to eat, or 6,000 years, who knows how old.
Yeah.
What happened? And that's still a bit of a mystery to this day. And that's like, it's like, you know, that's the awe and wonder that I appreciate about our world and about our experience, because there's so much we can't explain. And even if we have a genius or two that come along and give us explanations, you found out that some of that's just imaginary. And
Well,
maybe
I think that they're
Yeah.
inventions.
inventions, right?
Anytime when you create a model to explain something, that model is an invention.
Right.
You have to come back next week.
Yeah, we'll have to do another show.
Bring your whole thing there.
Yeah, thanks for watching, everybody. WATV Woodstock, Channel 23. And we've had Bob Lavaggi putting up with me for an hour. And thanks for the great conversation.
Thank
That
you,
was a lot of
George.
fun.
This was...
And I'd love to see this whole presentation sometime. I'm sorry we kind of just sort of left Einstein in the dust back here.
yeah.
But yeah, thanks.
Okay.
All right.
Thank you.
All right. Thanks.